Hello everyone, welcome to online classes DPS Siliguri for 2020-21. Myself Somnath sir, and today is my last lecture in this session, and this lecture is also very important. And today first we'll start with the electric potential energy. So what is the definition of electric potential energy? Electric potential energy of a system of point charges may be defined as the amount of work done in assembling the charge particle at their locations by bringing them in from infinity. So basically what do you mean by that is, suppose you have a charge particle Q1 and suppose you want to bring another charge particle from infinity to a point P, which is at a distance r from the charge particle. So for that you are doing some work done. So this work done is the potential energy. This work done is the potential energy. So this derivation now we know from my last lecture very well. We can derive it, and the value we know 1 by 4 pi epsilon naught. One is Q1, another one is Q2. The distances are, in the last one you have Q naught by R, that is only the difference. This is one type of definition. Another definition is that in some book, especially in some foreign writer book, you get the different definition exactly reverse. What is this? In this one we bring the charge particle from infinity to a point and the work done is called the potential energy, and in some foreign writer book you get exactly the reverse thing. In that one what happened, if you move a charge particle from R to infinity, then the negative of work done is the potential energy. That means you can say it in two ways. One is the potential energy is the negative of work done. Where the potential energy you are taking negative of work done, that means you are moving from R position to infinity. And in our Indian book, mostly like S.L. Arora, NCRT, they are just do the reverse thing. They are bring the charge particle from infinity to a point, and that's why this work done is the potential energy. So sometimes some student think in the contradiction way, in some writer use this one, in some use this one. So hope I'm able to clear it. If you move the particle from R to infinity, the work done, and the negative of that work done is the potential energy, and in some book it is written infinity to that point, then that work done is the potential energy. So indirectly both are the same meaning. Okay. So now this potential energy is, this work done is the potential energy. So as the potential energy, this work done is the potential energy. And one more important thing, very important, work done. This is very important. Why? Because Q1 is the charge particle and you bring the charge particle Q2 from infinity, and now you move from suppose R1 position to R2 position, and let the position is R1 to R2. And now examiner can ask you, when the charge particle move from Q2 R1 position to R2 position, what is the work done? So when this type of question you have, just not the only one position, you are from one point to another point, then the work done is change in potential energy, that is final potential energy minus initial potential energy. And you can write it in that way also, which charge particle you move. Say for here we move the Q2 charge particle, but in generalized form we can suppose that charge particle is Q charge. Here you can write Q2 also, but as I am trying to write the generalized equation, so I put the general charge particle Q and the final voltage minus initial voltage, a final potential minus initial potential. That is, we frequently use this formula. This one is very important. This one is very important for your entrance as well as board numerical, to solve board and entrance type numerical. Now one more thing which is very important, that is Suppose you have four charge particles, Q1, Q2, Q3, Q4. So now the question is that if you have more than two, like 3, 4, 5, 6, that type of charge particle, how many potential you have to choose at a time, or overall how many potential you have to choose. So see, what is the formula of potential energy? The formula is 1 by 4 pi epsilon naught Q1 Q2 by R square. That means for potential energy you need two charge particles at a time. So as two at a time, you have to use two at a time. You have to use you have to take the help of mathematics. And what is that? That is the combination NC2. Why? N is the availability and C is at a time you have to choose two. So what is the formula? Factorial N 2 N minus 2 I. So N into N minus 1 N minus 2 2 N minus 2. 2 into 1 is 2. So this is cancelled. So your answer is N minus 1 by 2. So that is the number of potential energy you have to choose at a time. If you are only bio student, means if you don't have maths, then don't go with this formula. Don't go with this formula, because this one is complicated thing for you. You just remember this value, okay, N into N minus 1 by 2. You can use this formula for in chemistry also. Suppose you have n number of electronic orbit is there, and electron can jump from one orbit to another orbit, then also you can use this formula. So this formula is very, very important. So according to this, how many charge particles you have? 4 charge particles is there. So what we use, 4 into 3 by 2, that is 6. So according to this formula, how many potential is there? You have to write 6 potential. See, one is between 1 and 4, one is between 3 and 4, one is between 2 and 3, one is between 1 and 2. How many you have? 4. Now you can use this one also 1, 3, and you can use this one also 2, 4. Similarly, in for atomic structure, which is you have in class 12 at the modern physics, and you have in chemistry also. Okay, suppose you have 1, 2, 3, 4. 4 orbit you have, and electron can jump from one orbit to another orbit. So how many spectral lines you have? See, the number is 4, so 4 n into n minus 1 by 2. So 4 into 3 by 2, you have 6. Let's check. 1 spectral line, 2 spectral line, 3 spectral line, 4 spectral line, 5 spectral line, 6 spectral line. So it will help you in that one also. Now I give you one numerical, then you understand why I'm saying that change in potential energy equals to work done is very, very important. Suppose you have 3 charge particles like 2 microcoulomb, 4 microcoulomb, minus 2 microcoulomb, and they are separated by distance 1 meter, 1 meter, 1 meter, where the position is A, B and C. And now this is the initial position. Now you move the charge particle from A to A dash, B to B dash, C to C dash. And now I can use the different color. Now the new positions are, suppose 2 meter, 2 meter, 2 meter. And the question, that means what has happened? You move A from A to A dash, B to B dash, and C to C dash. And what you have to find out? You have to find out the work done during the process. So now see how much easy this question is. Potential energy initial, this is the position. So 1 by 4 pi epsilon naught, you can take as a common part. Now this one and this one. So we can write 2 into 4 by the distance is 1 plus 4 into minus 2 by distance is 1 plus 2 into minus 2 by distance is 1 and micro into micro. So you can write 10 to the power minus 6. We know this 1 by 4 pi epsilon naught is 9 into 10 to the power 9. So 8 minus 4 into 10 to the power minus 6. This cancel. So 36 minus 36 into 10 to the power. Sorry, here we can write 12. Because micro into micro, so 10 to the power minus 3 joule. Now, final position. See, everything is same, just in case of 1 meter separation. Now the separation is 2 meter. So everything is same. 9 into 10 to the power 9, 8 by 2 minus 8 by 2 minus 4 by 2. So 9 into 10 to the power 9. 2, 8 minus 4, so that is 9 minus 18 into 10 to the power minus 3 joule. You can write directly also this one divided by 2, that is minus 18 into 10 to the power 3 joule. So what done? That is final potential energy minus initial potential energy minus 18 into 10 to the power minus 3 minus 36 into 10 to the power minus 3, that is 18 into 10 to the power minus 3 joule. So you understand how these relations are very, very important to solve numerical, and you can if you go through book, then you find so many numerical related with this potential energy, changing potential energy, work done and all. My next very, very important topic is relation between electric field and electric potential. So see, if you have a charge Q and if you bring a charge particle Q naught, so force is applied in this direction and you are moving in this direction. So what is the angle between them? 180 degree. So work done, that is F dot dr. Again I am saying, okay, I am trying to use your Indian book like S.L. Arora and NCRT, this type of book, because if you go through H.C. Burma and in other book like Rashmi Khaliday, so you get exactly the different way. Means in that case the potential energy is the negative of work done, and here the work done is the work done for a potential energy, because here we move in that direction, we bring from infinity to this, and they are doing from R to infinity. That is the only difference. Okay, so work done is F dot dr. Work done is F dot dr, and this F is so QE, and the angle between them is 180 degrees. So we can write one line also, F dr cos 180 degree. So minus QE dr, that will be equation number 1. And similarly, we know work done equals to charge into dV. So if we use this formula, so what we write, Q into dV, that is minus Q into E dr. So dV equals to minus E dr. From that we can say E equals to dV by dr minus with n cap. Now listen, electric field is a vector quantity, so we write E in the form of vector, and as it is a vector, so we write n cap. This one is very, very important, because this meaning, the meaning of this one is little bit different. I can try to explain it later on. And one more important formula related to that, which is very, very important. These both are very, very important. So I'm trying to solve one question from both. These two are the second one is you can write dV equals to minus E dot dr. Actually you can use this formula is also, and that's why a little bit of confusion, because Why this confusion is because here you move the charged particle from infinity to this, so this work done is this one, and actually what happened, the potential energy is the negative of work done. So but these two formula are very important for board exam as well as in entrance exam, and believe me, every alternative year in entrance exam also, even in IIT, every alternate year they give one question from this question. So you understand this one is board exam, for board exam as well as in entrance exam, very important. So we can try one question each from both the formula. My first question is electric field is given 2xi minus j plus 3z square k volt per meter. Potential at the origin is 10 volt. Find the potential. Find the potential at the point P equals to -2, 1, -1 meter. See, this one is one question. It's very important. Two type of question they can arise, examiner can arise. One, they can give you the electric field and they can ask you voltage, and the second one, they can give you voltage and they can ask you potential. So let's start with that numerical. We know dV equals to minus E dot dr. Now see, it's very important. As in this electric field, x-axis, y-axis and z-axis all are given, so that's why it's a little bit complicated, a little bit advanced level question, but now you all know, sometime 5 to 10 marks, even a very good level question is given in board exam also. So let R is a position, xi, yj, zk, then we can write dr is dxi, dyj, dzk. So now this dV equals to minus E, that is 2xi minus j plus 3z square k dot dxi dyj dzk. Now we know from the dot product of two vector, I dot I, j dot j, k dot k is 1, so we can write directly dx 2x dx plus dy minus 3z square dz. So that one we have minus 2x dx plus dy minus 3z square dz. Now if we take integration, what happened? dv, that is 2x dx plus dy minus 3z square dz. And see, this one is called triple integration, because you have x-axis variable, y-axis variable and z-axis variable. I think you don't have triple integration in your class 12 exam maths. I think not in your syllabus. If it is, then it's very good. But don't think it as a triple integration. Think it as a single integration. You just integrate x, you integrate y, and you integrate z. You all know very well how to integrate this. So with this, it's starting from the origin. Origin means 0, 0, 0, and the point is minus 2, 1 and 1. So that means if you consider 0, 0, 0, that means x-axis is 0, y-axis is 0, z-axis is 0, and if you consider this one minus 2, 1, minus 2, so your x-axis is minus 2, y-axis is 1, z-axis is minus 1. So basically what happened, your coordinates are 0 to minus 2, 0 to 1, 0 to minus 1, and here you starting from origin, and how much is the value given in the origin? We put it later on. So V, that is V0 Vp, that is 2 x square by 2, 0 to minus 2, y 0 to 1, 3 x cube by 3, 0 to minus 1. So upper limit minus lower limit v0 is equals to this 2 cancel, this 3 cancel. So what we have, minus 2 square minus 0 plus 1 minus 0 minus 1 cube minus 0. So what we have, minus 4 plus 1 plus 1. I think it's plus 1. So what you have, 4. So not 4, sorry, 2. So Vp and voltage at the origin is 0. Sometimes they can give you 0 volt, sometimes they can give you another volt. Whatever be the voltage, it doesn't matter. You put it, that is equals to minus 2. So potential at P is 10 minus 2, that is 8 volts. So you understand how much important or how much interesting this question is. My second question is question number 2. V is equals to 2x square minus 3y plus z cube volt. Find electric field at P, which is minus 2 to 1 meter. So now it's exactly the reverse question. In the last question, electric field is given, you have to find out the voltage, and in this question, voltage is given, you have to find out the electric field. So whenever you have this, from the formula of electric field, we know dV by dr in cap, and in that time I'm saying you in detail we derive it later on, means we discuss it later on. What do you mean by this? This means dV by dx I, dV by dy j, dV by dz k. That means you have to differentiate, that is called the partial differentiation. You have to differentiate partially, one by one. When you differentiate with respect to x, keeping y and z constant. When you differentiate y, keeping x and z constant. When you differentiate z, keeping x and y constant. So here in this one, voltage is given. So first of all, we have to differentiate voltage with respect to x. And when you differentiate voltage with respect to x, keeping y and z constant. So these two are constant, so 0. So what we have, 2x square. So what we have, 4x after differentiation. Similarly, if we differentiate voltage with respect to y, when you differentiate voltage with respect to y, keeping x and z constant, so x and z is 0. So now y, the differentiation of dy by dy is 1. So what you have, minus 3. Similarly, if you differentiate voltage with respect to z, what happened? When you differentiate z, keeping x and y constant, so what you have, 3z square. So now our electric field is minus 4xi plus, or you can put minus 3j plus 3z square k, which is minus 4xi plus 3j minus 3z square k is your electric field. Now it's a vector form, and according to question you have to find out the electric field at point P, which is minus 2 and 1. So on that basis, if we put this value, electric field at P, that is minus 4 into x coordinate is minus 2 plus 3, y coordinate is 2, but here no y variable is there. As no y variable is there, it is yj, means it is j, and minus 3z. What is the value of the z coordinate? 1. So what you write? 1 square k. So what you have? Sorry, I missed I. So 8i plus 3j minus 3k Newton per Coulomb. Now, if you want to find out the magnitude of electric field at P, that means 8 square plus 3 square plus minus 3 square. So 8, 64, 9, 9, 20. I think 82. 82 Newton per Coulomb is the answer. So you understand how good this question is, how conceptual this question is. So try this type of question. It's a very, very important, and so many examples you have in your book, and I'm also trying to give 1 or 2 questions related to this one in your assignment. After that part, now a very, very important topic which is especially related to your board exam is equipotential surface. So what do you mean by equipotential surface? Equipotential surface are those surface throughout which potential remain constant. I repeat, equipotential surface are those surface throughout which potential remain constant. Indirectly, you can say all Gaussian surfaces are equipotential surfaces. Now, in exam, examiner can ask you the definition of equipotential surface. They can ask you properties of equipotential surface, which is very, very important. So, first property is equipotential surfaces are those surfaces throughout which the potential remain constant. This is one property. Means you can write the definition. Second property is electric field always normal to the equipotential surface. Means suppose you have a charged particle and this one is your equipotential surface. So electric field is normal to the surface. See, electric field is normal to the surface. And if you ask why, I can just say you this one here. It's minus dv by dr with n cap. So tangent and normal, slope m1 and m2 equals to -1. Then they are perpendicular to each other. That one is the reason behind that. Third point is that that's the second point. Electric field is normal to the equipotential surface. Third important point is that if you move from one point to another point in same equipotential surface, work done is 0. Very simple thing. Suppose for this equipotential surface, the voltage is 10 volt. Means throughout the surface, the voltage is 10 volt. So if you move from one point to another point, so your work done is charge into change in potential, charge into final voltage minus initial voltage, according to this VB minus VA, that is charge into 10 volt minus 10 volt. So the answer is 0. So if you move from one point to another point in same equipotential surface, your work done is 0. Then the next thing is draw equipotential surface. Then the next thing is draw equipotential surface, which is also very, very important. Draw equipotential surface. So first we can draw for point charge. Suppose we have a point charge. So these are the equipotential surface. This one is one equipotential surface. This one is one more equipotential surface. So we have two equipotential surface. Now electric field is normal to the equipotential surface. Electric field is normal to the equipotential surface. So what we can say, these are the electric field, and these are the equipotential surface. This is for the first one. The second one is Draw equipotential surface. Draw equipotential surface for line charge. Draw equipotential surface for line charge. So if you have a line charge, your equipotential surface is cylindrical. So it will look like this. It will look like this. Means this one is one equipotential surface, this one is another equipotential surface. Don't confuse, don't think both are the same equipotential surface. They are two different. Suppose this one is 10 volt, this one is 5 volt. So they are different equipotential surface. Now, electric field is normal to the equipotential surface. So this one is the electric field. See, normal to the equipotential surface. This one is the second one. Next, the third one is draw equipotential surface. The third one is very, very important. Draw equipotential surface. Examiner can ask you for uniform electric field, or they ask you draw equipotential surface for infinitely long sheet. They can ask you both way. They can ask you for infinitely long sheet, or they can ask you for uniform electric field. So for uniform electric field, we know, or infinitely long sheet, if they are asked, because electric field is uniform, these are the equipotential surface. So these are equipotential surface. And these are the electric field. And the last one is draw equipotential surface for electric dipole. Draw equipotential surface for electric dipole. Means you have a plus charge, you have a minus charge. So it's very simple. First, make them in that way, dotted line. And now we know the direction of electric field from positive to negative. Plus to minus. So this one is electric field, and this one is equipotential surface. Okay, and with this I just want to discuss just one more point, which is very, very important, and then I conclude my lecture today. The last thing, suppose we have a shell, okay, so if Q charge is distributed throughout the surface, so we know electric field is look like this. R equals to capital R, smaller greater than capital R, smaller less than capital R. Electric field is inversely proportional to R square. This one is 1 by 4 pi epsilon naught Q by R square. Okay, and now because now we know that's what I'm saying. It's a very, very important. Electric field is minus dV by dr with area. That means differentiation of voltage with respect to position is your electric field. Now see, from 0 to the surface, your electric field is 0. When 0 to the surface, electric field is 0, we know the differentiation of constant is 0. So that means in terms of potential, what we can say, from the center up to the surface, potential is remain constant. It's very, very important, and this one is used in the next chapter. Means next topic is capacitor, where this one is used in very frequently. This concept is used. That's why I'm trying to explain it. from the center up to the surface, as the electric field is 0, so your electric potential is constant. So V is 1 by 4 pi epsilon naught Q by R, and outside this electric potential is inversely proportional to R. So this is the graph of potential, capital R, small. So what happens if from the center up to the surface potential remains constant, and outside the surface means you can write in that way 1 by 4 pi epsilon naught Q by R when R is 0 to up to the surface. V is 1 by 4 pi epsilon naught Q by smaller when R is greater than capital outside the surface. So this one is called shell. You can try, especially those are interested for entrance exam and all, you can try same thing for electric potential for the solid sphere of non-conducting, because for conductor is same, for non-conductor you can try, because it's a very important for entrance exam like IIT and all. This type of concept is very important. The potential, electric potential for non-conducting sphere. Okay, so today I conclude my lecture here and hope you all enjoyed during that five days and 5 class. And the most important is, again today I also on the basis of that lecture giving some what you call a worksheet, and you submit, you try to solve it, and then you submit it to your or mail it to your respective teachers. And hope you are in your home and enjoy this this quarantine and all. Bye. Good night.